So we're getting ready to start chapter 21. I'm going to have to go through this a little quicker than usual since YouTube has length caps, but just at any point periodically throughout the video, please ask the sub to just kind of pause so you guys can jot down what I'm writing down as you see fit. Okay, so in the last chapter, we were faced with questions like we took a sample, we thought this was the true proportion, we saw this sample proportion. Has the proportion actually changed? So we were looking at hypothesis tests, and those hypothesis tests revolve around this normal curve. So the normal curve, once we've met the conditions, says how unusual certain sample proportions would be to C. And so that follows the distribution centered at P, which is your population parameter, and then our standard deviation is calculated using P, Q, and N. Okay, so the new question we're faced with is comparing groups of individuals and seeing if there's a difference in proportion. So for example, do men and women wear seatbelts the same percentage of the time? So we take a simple random sample of 200 male drivers and another simple random sample of 250 female drivers. So we see that 146 men wear their seatbelts and 203 women wear their seatbelts. So we want to know, is there a significant difference between the two genders, or if there's any difference at all? So we're given a little more information here. So let's go ahead and look at this first number, 200. So 200 male drivers. I'm going to call my males group 1. So N1, the sample size for that first group, is 200. Okay? Simple random sample of 250 female drivers. Female drivers, I'm going to call that group 2. Okay, so then this 250, that's going to be N2. All right, so the 146 men wearing their seatbelts represents the amount of successes, if we can still think of those as in terms of successes. And so I would call that my X1. So X1 would be 146. And then this would give me my sample proportion for males. And I might write it like that, or I might choose to write it like that. Okay, and so I would just calculate that as 146 out of 200. And for group 2, for the female drivers, I saw 203 out of 250. So X2, the amount of successes I saw in that second group, would be 203. And now you'll see later on why I'm writing out the number of successes, and that has to do with how we enter it into the calculator. But we can still calculate the sample proportion the same way we saw last chapter. So again, I can write this as P subscript F or subscript 2, just something to keep track of the two separate sample proportions that I'm calculating. So P2 I would just calculate as 203 out of 250. So we see here that a larger proportion of females admit to wearing their seatbelt regularly, but is that necessarily a significant difference? And is there necessarily a difference at all, or is it just sampling variability? So that's kind of the question we're faced with in this chapter. So before I jump into doing anything with these numbers, just like we saw in the last chapter with this sampling distribution, it's going to follow a normal curve only after I've shown that it meets the proper conditions. And so the good news is 3 of the 4 conditions are identical to the ones you've already seen, but there's one new one. And so that new condition states that the 2 groups must be independent of each other. So we can't sample a bunch of males and have that be group 1, and then in group 2 with the females, we can't know that, I don't know, there's a bunch of married couples and they've been split up into these 2 groups because they're no longer independent of each other. And so that's what I'm referring to here with this condition. So I have to know the two groups are independent of each other. That is critical. So that's got to be the first one we check from now on. And then the conditions just need to be checked for each group. So my male sample needs to be a simple random sample. My female sample needs to be a simple random sample, and so on and so forth. So what we're looking at is SRS of group 1, and we need SRS of group 2. Okay, so we need to calculate, for this example we just saw above, I only had, let me start that over. I was given a p hat. There was no, we believe men wear their seatbelt this much. I wasn't given that for this problem, so anytime I'm not given a p, I just estimate with p hat. So I have to, in group 1, see at least 10 successes and at least 10 failures. So I want to see at least 10 males that admit to wearing their seatbelt and 10 males that admit to not wearing their seatbelt. Okay, same thing over here in the second group, so N2, however large that second sample size is, I need to see at least 10 people who admit, 10 females who admit to wearing their seatbelt, and I would need to see 10 females who admit to not wearing their seatbelt, so that's Q hat. So I have to check that twice, one for each sample. And finally, our 10% condition. So our 10% condition just says that N1 needs to stay under 10% of the group 1 population, and N2 needs to stay under 10% of the group 2 population. So we'd look back at that sample and we would ask if we stayed under 10% of male drivers, so group 1's population, and we'd ask ourselves if N2, the sample size of the females, if that stayed under the female driver population. And so we see that we're well within reason for this specific problem, but we're going to actually come back to the seatbelt problem later on in the note. So just to recap, these 3 conditions, 1, 2, 3, are identical to the ones we've seen before, but I have to do them twice. So I have to do them for group 1 and I have to do them for group 2. And then we just added this new one that I have to state the 2 groups are independent of each other. So no married couples, no brothers and sisters. And oftentimes in real life we can't check this, so it's going to be typical to just say assume the 2 groups are independent of each other. Okay, so flipping the page over. For this particular problem, we would want to conduct a 2 proportion Z interval. And so since we've already checked our conditions, we know that the population is going to follow a normal model. So 2 proportion Z interval. So this should look familiar. We have done a bunch of 1 proportion Z intervals. Well, now we've got 2 proportions. So the distribution is going to be centered at the true difference, so P1 minus P2, whatever that difference is. So that's our mean. And we imagine this curve just like we imagined it for the last chapter, where all of these were little sample proportions in here. Well, now it's the difference between sample proportions. So this is, I went out and I asked 200 males, and I went out and I asked 250 females, and I subtracted the difference from these sample proportions. So I went out and I asked 200 males, I went out and I asked 250 females, and I took the difference of the sample proportions. And so those differences, I'll write that down, those differences are what represent the data underneath the curve. Okay, so that's the only difference. We're looking at differences. Now, where does the standard deviation come into play? If we remember standard deviation from a couple chapters ago, you guys don't have to write this down necessarily, but just a little bit of background. Your book refers to it, and many other books refer to it as the Pythagorean theorem of statistics. And so when we see x and y are independent variables, we've seen this before. The standard deviation of x and the standard deviation of y, combine those and we get standard deviation x squared plus standard deviation y squared. So just like Pythagorean theorem only works on right triangles, this formula that I'm about to show you only works when the variables are independent. Okay, so the formula we saw was when we were looking for combining, random variables and when we were looking for finding the difference between random variables. And we ended up with a formula that looked like this. We saw sigma for that x variable squared plus sigma for that y variable squared. And that gave us either the sum or differences of those two random variable standard deviations. So that's kind of where this formula comes into play. Just a little recap there. The formula for standard deviation is going to be the square root of P1 Q1 over N1 plus P2 Q2 over N2. Okay, and so that just tells us how many, well, we always go out 3 tick marks, but that just tells us how big these tick marks are away from each other. That's your standard deviation. Okay, when we don't know the true parameter, when we don't know the true proportion of men that wear their seatbelts or the true proportion of women that wear their seatbelts, that's when we estimate this value. We estimate the standard deviation with something called the standard error. So standard error, you may or may not see where I'm going here. Exact same formula, but now we're estimating with whatever we observed in our sample. So we have our sample p hat for the first group, our sample q hat for the first group, divided by how many people were in that first group. And then same thing over here for whatever the second group is. Okay, so once we've met all 3 of these conditions, we get to say that the distribution of the difference between sample proportions, so that's up here, that's all these data values, the difference in sample proportions. So we get to say that this data follows this distribution. It follows P1 minus P2, and then it's going to have a standard deviation, which we may or may not be able to calculate. We may just have to estimate it, but this, if we do know, is what it would follow. Okay. Again, please pause the video, ask the sub to just hit pause while you guys jot this down as needed. So I'm going to keep going, but stop whenever you feel like you are writing too quick. Okay, so for actually creating these confidence intervals, the same thing we saw from the last chapter, you don't have to write this down. We would take our estimate and we would add a margin of error in both directions. So we had our p hat, and then we threw our arms out, and we hoped to try to capture that true p. Okay, so on the AP test, you're provided something similar to that. What they choose to give you as far as confidence interval formulas is you have some statistic. Remember, a statistic is something you've calculated. So a sample proportion or a sample mean statistic, something you've calculated. And then we add and subtract a critical value. And that critical value gets multiplied by the standard deviation of whatever statistic it was you calculated. Okay? And so just to add a little more understanding to what it was that all of these things represent. So the statistic, this is something you've calculated. Critical value, this is your Z star based on your confidence level. And then over here, this is just going to be our standard error. Okay, so again, that stuff in green is what you'll be provided with on the AP test as far as what they give you to try to jog your memory of how to calculate these things. So just so you've had some exposure to that. So how do we calculate it? Well, we calculate it using our statistics. So we observed this difference. We saw in our sample that the proportion from this first group and the proportion for the second group, there was that big of a difference. And then I'm going to get a Z star based on whatever confidence level I have. And then I use the standard deviation of the statistic. So the standard deviation of the statistic, well, the statistic here is p hat 1 minus p hat 2. The standard deviation of that is that square root stuff. So I have square root of p hat 1 q hat 1 over n1 plus the sample proportion for the second group over how many people were in the second group. Okay, same setup as before. We have our observed difference, our observed statistic, and then I have a margin of error. That I add in both directions. All right, I'm going to go ahead and stop the video here so that I don't exceed the file size limit, but I'll just go ahead and pick back up on the next page so you guys will just start a new video.